Good morning, everyone. Welcome to the third video on the one concept and many tools, simulation tools. And today I'll be discussing about the main concept, which is on circular motion. There are two types of circular motion, as we all know. One is the horizontal circular motion. The other one is your vertical circular motion. So we'll be looking at both of them. As I had already told you in my first video itself, I'm not doing any math, nor I'm teaching you any concept over here, which as all teachers, we all know what is it about. I'm just showcasing you what are the different tools that we have to teach this particular concept, which will be useful while we start teaching in our classes. And how do we start applying these tools? So I'll just give you a demo based on this. And as I had already told you, I'm not an ambassador or I'm not doing any marketing for them. But I found that such tools are really useful, which are free of cost available for academicians. So I'm continuing with this. Okay, so with this brief introduction, let me continue with this. Let me share my screen. Right. The circular motion, as you know, this motion doesn't tell you whether it is a horizontal or a vertical circular motion. Because when you talk about vertical circular motion, you bring into an element of gravity over here. You consider there is an element of gravity also acting due to Earth or maybe some other planet. But here what we do is, so it does not consider the gravity effect. Now, so as you see a particle moving in a circular motion over here, the acceleration is shown, net force is shown over here. And there's a speed element which can be adjusted. And you can also show something like the radius and mass over here, you can adjust over here. Okay, let me change any one of these parameters to get a clarity of this. Now let us say, for example, I might reduce the font a little bit. Right. Now, if I increase the speed, now what will happen? So for example, if I want to increase the speed, I can increase like this. So as you see, as I'm increasing the speed from 26 to 29 over here, I see the net force also keeps on increasing because the centripetal force is directly is equal to mv squared divided by r. When v increases, this also increases. This is being shown over here. And you know the acceleration is also increasing. See, it is 16 meter per second square. If I reduce it, for example, this becomes 15 over here. If I still reduce it, 14 over here. So thus it keeps on. These two parameters changes when the speed is increased or decreased. Now when I increase the radius, for example, radius is 40 meters. Let me choose this. Now when I increase the radius, so what do you observe? You observe it becomes 42. This is 330 and 17 meter per second square. When I increase it much more, what happens? The force is decreasing, the acceleration is remaining a constant, but anyway, it's not remaining because it has to show the significant figure, right? So it could be something like 18 it was earlier, it could be something like around 17.2 or 17.4, and it is not able to show a decimal place, so it is just showing 17 over here. Then comes 16, 15, see, it remains the same and so on. So you can ask this as a question to find out, okay, why does this happen? Is it a glitch in the software, or is it something because at certain values of the radius, this does not happen? So you can ask this one to them. Okay, they'll definitely be able to, they should be able to answer it. Okay, in a similar way, you can also vary the mass. Now let me go on to the next video. So this simulation only helped you to find out how does the circular motion, okay, the horizontal circular motion, I'm not looking at vertical circular motion. Okay, so though the circle is shown from a vertical perspective, this is not a vertical circular motion. Reason is because I'm looking at it from the top and there is no component of mg acting over here. Okay, if there's a component of mg acting over here, definitely you can say the vertical circular motion. Okay, you can just say it is uniform circular motion. Now let us go on to the next one. The next one shows you something like the circular motion once again, and once again there is no mass anywhere to be shown over here. And shown here is a simulation from GeoGebra. If you are very good in GeoGebra, in fact, you can yourself design such simulations and you can show it to them. Okay, now, so you have a start button here. There are sliders which are kept over here, very similar to what you had done in the previous simulation. The only difference in this is this particular button, cut the rope. Okay, let me do it first. Now, let me start the simulation. And one more difference is that to indicate the vectors, vectors are very important when it comes to IB level to understand, okay, where is the force acting, to draw the free body diagrams and so on. Let me start with this. When you start this, as you see, you can very clearly show, okay, what is the net force acting, because many students make a mistake here. Let me first close this because this is slowing down my simulation. Okay, let me start here. Right, I don't know why it's not moving. Let me refresh this once again so that it runs on hand. Okay, now it's opening. So vectors are very important for anyone to work with. Okay, when you do the chapter on forces. So let me start with this. Let me click on, okay, start over here. So as you see, most of students will say, when you ask about what is the force acting on the particle, they always get confused and say the particle's force at this point, for example, point A, it has been acting like this, okay, towards right. That is incorrect. Okay, they should clearly know what's happening over there. It is not acting like that. It is always acting towards the center, which should be indicated like this over here. So in fact, you can change the values of mass, velocity, radius, and so on. Okay, so I should show the acceleration here, centripetal force here. Okay, so the directions are shown over here. Right, now what I do is, let us say, for example, it's pause, it's a reset. Let me reset this. Let me click on start once again, and I cut the rope. When I cut the rope, what happens? The particle is going in a tangential line over here. Okay, anywhere when I cut the rope, what happens is automatically the particle moves along the tangent. It does not move in this direction. Okay, let me reset this once again. Let me run this simulation once again. Let us say I cut the rope somewhere here. Now what does it do? It doesn't complete the circle. The place where it has been cut, the particle actually starts moving. The rope is cut here, the particle is moving like this. Okay, so these kinds of information, okay, would be shown with the help of a simulation where the student will understand how to draw the forces and how to work with the free body diagrams. Okay, now let us move on to the next simulation. I have copied all the links somewhere. Next simulation is about conditions for a uniform circular motion. Now what I do is, there's an angle here. Okay, what I will do is I'll change the angle here. Okay, if I change the angle to be minus 170, what is this angle here? Angle is equal to motion, but angle between the motion and the force. Okay, the displacement of the force. Let me keep it initially not 170. Let me keep it here. Minus 100. Let me start with minus 100. And let me click on this non-stop button over here. Now what do you observe? You see, okay, the particle started from here and it keeps on moving like this over here. If you still want to see what is the angle, how does it denote over here? Let me keep it over here. Say for example, minus 80. Now what is the angle here? Or maybe I'll take minus 90 here. I missed this spot. Minus 90. So what is this now here? What is blue here? Motion. Motion, that means the particle is initially moving like this. What is the force acting? Force is acting perpendicular to it. When this happens, now what happens to the particle's trajectory? Okay, that's what we are going to ask. So when they are perpendicular to each other, what's seen? You can see a circular motion to be seen. Under what conditions a particle will move in a circle? Under what conditions a particle will not move in a circle? That's what we can show from here. Now let us say, for example, if I increase this angle, let us say instead of minus 90, I make it as minus 80. One more step I put it. Okay, small difference. Do you think it will move in circular motion? It won't move in circular motion. Let me click on this and show. It is moving in a circle, but it is not completely circle. It is going something like an outward bound spiral. Okay, if I still reduce it, minus 80 to minus 70, the spiral's radius increases. Okay, it is going outwards. Now minus 50, again it goes away. You are not able to see it in the screen, right? Now can I reduce it? No, I can't reduce this, I think. No, I can't reduce it. Okay, now what I will do is, let me increase it to minus 20, minus 10. Now what do you think will happen? See, this is the motion and this is force acting on it. Okay, an object is moving like this and you are also applying force along the direction. Then the object will move in a straight line. Let us do this. Let me keep it here. Okay, minus 10 only. It's almost going in a straight line. It's not a straight line, it's a curved path. Now let me make it 0. When I make it 0, now what do you observe? It goes in a straight line. Now why is it that there are dots, and these dots are seen to be something like the distance between them is much larger. Every time the distance is increasing. What does it tell you? It tells you that there is something like a constant force acting. That means the particle is moving under acceleration, right? So many things you can convey just by looking visually. Okay, so teaching physics visually is always useful like this. Okay, now what I will do is, let me increase this value 20 degrees, for example. Now earlier minus 20, what it was happening? It was going like this. Okay, it was going in an anti-clockwise. And plus 20, it is going in the clockwise direction. Now let me increase it to some more higher at 80. Now, see, it's going in an outward bound spiral over here. 120. Okay, let me move it at 90 over here. So what is that you expect in 90? 90 should be circular motion, perfect circular motion. Okay. Now what I will do is, can I move it? I cannot move it here. Okay, let me move it to 100. Now what do you expect? Once again a spiral, but it is spiraling inwards. Okay. If the angle between the force and the motion is above 90 degrees, then it's an inward spiraling motion. If it is below 90 degrees, then it is outward spiraling motion. That's what you can understand from here, right? And then you can ask the students, why does it happen? Because they already learned the M1 mathematics over there. You can ask them to find out, okay, what is the reason behind it? Then now let me increase it a little bit more. Once again, you see, so the spiral once again goes like this. For any angle that you do, it will always be outward spiral. Now what I'll do is I'll make it to 170. What's happening over here? So the particles force motion is like this, but the force has been acting in the opposite direction. And when it comes like this, it again comes back like this. So there's something like moving in this direction. So it is at the same point over here. Right. Let me go on to the next simulation. Now this one. What is this? Again, we are only looking at circular motions which are horizontal. No effect of gravity over here. Now here you see there's something like you have a horizontal tray and there is something like an object which has been connected to this. And you can animate this one here. So as this starts rotating, okay, the object starts rotating over here. Okay, along with this, the angle is given in terms of degrees and as well as radius. You can find out the time period, you can do angular speed, you can find out and so on. Now, one beauty of this one is that I can toggle this like this. Okay, why is this useful? I'll tell you one thing here. See, if I look at it from this perspective, I am able to see that the particle is now rotating in a clockwise direction. Now, if I turn this table on the other side, what do you see? You see that the particle is moving in an anti-clockwise direction. So therefore, when I say something about the angular velocity vector, now angular velocity vector, before you define, you need to define, okay, which direction, okay, is positive, which direction is negative. So what we usually do, we use our right hand rule to show that, okay, when the particle is rotating in this direction, okay, this is my right hand, okay, as seen in the video, it is left hand for you. Okay, so when I move it in a right hand direction, when the particle is going in a right hand, in an anti-clockwise rotation, then the thumb which is pointing towards me gives me the angular velocity vector. Okay, this is what it tells you. Okay, so in order to depict that, okay, so I just use this one here. And if at all, if you change this notation, instead of your right hand, if you use your left hand, then what can happen? This is a clockwise motion. Once again, it will be showing towards you, but this will be incorrect for you. Okay, so therefore use only one notation. So importance of notation, I depict it across. Okay, how to use the which rule and how to use the appropriate rule. Okay, in physics it's very important. You have many things that you can learn visually, but at the same time learn it appropriately, learn it correctly. That's very, very important. That's what we do using this. Okay, let me close this and go on to the next one. Now this one, okay, is an application of it. Okay, so this is very, very important. So in fact, I say everything to be important anyway. Now here what I do is I just reset this. I'll reset this. The particle is kept on the table and there is a friction. The table is being rough over here and there's an mg force acting on this. There's a normal force acting here. It's a friction acting here. The value of the friction is given. The coefficient of friction is 0.8 and the radius of the turntable. This is a turntable over here. The table is being this much longer. Is a complete radius of it. I am kept it very much nearby to center, maybe halfway between the center and the periphery of the disk. I kept it over here. And then what I do is I give a force. Now, how do I give a force? I give a force which is made to rotate like this. Which force is this? This is your force of rotation. So as this starts rotating like this over here, then what happens is there is a centripetal force acting over here. Okay, and the centrifugal force acts on the body. Then what happens is, if that force, outward force, is equal to the frictional force, the object will stay at rest. If it is more than that, the object will start flying away from here. Okay, so this you can do it at home also. If you have a disk and you take a small paper piece and drop onto it in a rotating disk, when the disk is rotating like this, take a small paper piece and drop on top of it. As it rotates, when the speed of rotation is higher, then the particle will just move away from it, right? So this is what is being shown over here. So this is a plot of force versus time. Okay, and how does the frictional force act over here? Let me start this, click on play. So initially, as the particle is rotating, the same force has been applied. When the same applied force is constant force over here, the frictional force keeps on increasing. It goes to a maximum, right? There's nothing but a static region of friction. And after that, okay, it immediately drops down. What happens? The particles start sliding. It crosses the limiting friction, and thereby the particles start sliding, and then it moves away from here. The moment it moves out of the surface, what happens? There is no force of the friction acting, so frictional force becomes zero. Okay, and the pink line over here denotes the frictional force. The red line over here denotes the static force. That is the force that has been applied on the object. And this line, this is about the time axis over here. Okay, it's one of the wonderful depictions that I found out. Okay, if I give this problem as a numerical to a student, okay, it will take a long time to solve. Sometimes he will be able to solve, sometimes he might make a mistake. So solving structured problems, in order to introduce how to solve a structured problem, okay, first thing is one has to visualize it. To visualize this, these kinds of graphs would be very much useful, right? If I now I can reduce this step also. For example, I can reduce this step a little bit more, reset this, reduce it less, and let me click on press over here. So it goes slower over here. So shows like, okay, what's happening to the object. The object is not moving over here. The moment it touches here, see, the object slides and moves away from you, right? The same thing is happening over here, so that can be shown, right? So this depicts about how circular motion and friction can be linked together. Next. This is a page that I found interesting. All the links will be shown to you in the video itself. So this tells you about what is your circular motion lab. Okay, what are the simulations that one can use over here, and there are some activities which are being given over here. Okay, one can use these activities, okay, and then start learning. This could be something like an experiment instead of you designing an experiment. So the experiment has already been designed. What to do, how to start with it, how to go with it, what is that you need to measure. Everything has been given over here. You can use this as an exercise, as an FA, okay, for your students to give it to them, and so they'll be able to complete this. Okay, so this is what it is. There are several experiments that are being varying radius, varying rotational speed, and then do it. Okay, there's nothing but what we have already seen over here, but the same thing can be given as an experiment, and the students can tabulate the readings, and they can understand what they're doing. They can plot a graph, okay, they can do all these things. This is how it has been useful. This also. Now comes the next one. Okay, this is a simple experiment which you can actually do it in a lab. So what you do is here is that you have a pipe, a PVC pipe can be taken over here, and there's a string which has been connected between these two. There are two objects fastened or been connected between here and then this point over here. And then what you do is you start rotating this. Okay, let me click on the start over here. So what happens over here? This starts moving, okay, in a circle, and this has been kept over here. And as a result of it, the time taken by it has been noted down, the radius has been given over here. Now, what I will do is, if I increase the weight here, if I increase the weight, then what will happen? Say, for example, it was 3 washes, now I made it 5 washes over here. Okay, then what would be the radius? The radius will change. If I still keep on increasing it, okay, if I keep on increasing it from 5 washes, just a minute, I don't know why it is not increasing here. Maybe, just a minute. I need to reset this. And then increase it. So it's just try 3 to 5. Now I have made 7 over here. See, when it was 5, the reading here, the centimeter reading here was seen to be how much? 0 to something like around 100. This is 150, 130 over here. Now I had put this here. Now let us see what is the radius here. It's again the same, but the time taken will change, right? Time taken will change. So why does the time taken changes over here? Okay, that is the question we need to ask. Okay, so when time changes, though you are increasing something, why does the time change over here? Let me reset this once again. Let me increase it a little bit more. 11 washes. The distance is same. Now what do you expect for the time? It was around 2.7, 2.8, right? Let me do it once again. 2.7, and this is 5.3. Or maybe I need to reset this once again. That'll be better instead of subtracting it. Just a minute. Wait. Let me start from the beginning. 2.8 seconds. Reset it. Second trial. 2.7 seconds. It just started once again. Array, I missed it. Sorry. 2.7 seconds. Okay. Anyway, roughly it's around 2.7 seconds for 11 washes over here. Let me reset this. Let me increase the number of washes, 11 to 17. I have increased 6 washes over here, which means the mass is still increased. Let me start this. Remember, earlier the time period was 2.7 seconds for one complete rotation, right? Now let me increase this and find out what happens over here. 2 seconds. That means the time period is reducing. Why does the time period reduce? Okay, this question can be ask them to arrive at the relevant math behind it and then do it. So they can say, as this increases, the tension increases, and this plays a direct role on this m omega square r, right? So m omega square by r, m v square by r, you can use it, okay, and then you can find out how does it depend on it. Okay, so again, a mathematical formulation one can arrive at it. Okay, this can be done over here. Now, next what I will do is, in fact, I can also change this also. I'll show you one more thing, what you can change here. So just sticker here, right? I'll do one thing. I'll click this reset over here. When I click this reset, you see there are moving masses, 146 grams. Okay, it has been given over here. I can change this also. If I want to change the radius, I can click here. When I click here, now you see it's increasing. The radius is increasing. Okay, so there is no left and right click. There is only one type of click. Okay, so if I keep on clicking it consecutively, the radius keeps on increasing. Okay, radius keeps on increasing like this. But if I again redo it, so it goes until a maximum and once again becomes 0 over here. So you can do this. Okay, and then you can also increase this also. Okay, moving mass. Which is this moving mass? This is the moving mass. This is stationary mass. This is the washer is a stationary mass where you click on the washer. And if you want to move this one, you can click here. See, you can click here, 232, 250, and so on. Now you have increased. The maximum is 250 over here. Okay, if I run this now what do you observe? You see, the speed is much higher, right? So you can do all this, okay, using this, and you can ask them to plot a graph on it, and then ask them, okay, what is your hypothesis? What is your RQ? Okay, so like this, you can use this as a mini, what you call a simulator engine, or maybe an IA, okay, to ask them to work on this. This will definitely help your students, okay, to perform experiments and to understand how to perform an IA appropriately, to how to write down an appropriate RQ. Okay, let me go on to the next one. This question, this particular simulation is very similar to what we have seen. All this we've been doing only with respect to circular motion, no vertical. It's only about a horizontal circular motion, which has been shown from different angles. Now shown here are the mg value, which is a mg here, this yellow color one, this is your mg over here, and then what else has been shown? Newton tension over here, tension acting on it, all this has been shown over here. Okay, what you are free to change, the value of m you are free to change, and then value of small m also you can change, radius you can change, this capital M, this small m you can change, and the wonderful thing is you can actually rotate it. I don't know why I'm not able to do this. Yesterday I tried simulating all of them. Now there is a button here, okay, which is pause. Now you have to play over here. When I play here, bring this one back here. Don't mistake this one to be that of a gravity or anything like this. I'm using my scroll button to scroll it inwards so that I can reduce the size. You see, this is what I have seen, right? So I'm able to do this. The same experiment what was seen in the earlier simulation, same thing. Only thing is, okay, I will be able to see it from both the point of view. Okay, and then this is quite interesting for me. So I can keep it like this over here, and then I can change the values over here. Okay, you can either give this one, you can find out what is the tension over here, and I can increase the mass or decrease the mass. For example, here I'm decreasing the mass. As I'm decreasing the mass, what's happening to the tension? There, in that previous simulation, you did not have an option to record this value of tension. Now, with the changes in masses, you are able to record the values of tension. That is what is the usefulness of it. Now, you can also change this M, and you can find out, okay, what happens to the tension over here. Okay, this M and this M changes. Any of this M changes, this definitely changes, and the angle also changes over here. The value of omega changes, the value of A changes, everything changes over here. Okay, so you can also use this one. Okay, interactively, you need to write the question appropriately so that you can use the simulation to make them understand. Let me close this. Let me take up this one. This is about a conical problem, conical pendulum. What does a conical pendulum do? Conical pendulum is not something like the point of contact, the point of support and the rotational bob, they are not in the single plane, right? So this is describing a different circle over here. Okay, so this you can use it. Okay, many times in IB question papers also you have seen some kind of questions like this. This would be like, for example, you had one problem in 2017 or 18 paper. I remember it was on a hemispherical ball. Okay, you have a marble and the marble is rotating on a hemispherical ball. These problems are very similar to this. Okay, so you can change anything here. You can change anything here. Let us say, for example, if I change the length over here. Okay, initial length is so much. Now I can change the length here. I can keep it exactly like this. Say, as I keep it here, it will be much more faster. If I keep it nearby to me here, you see 0.67 meters over here, then, so what is 0.67? And here it was 0.7 to 0.73 over here. Okay, the angle based on this, okay, how does the time of rotation change? Okay, and then you can change the tension over here. Okay, so tension here, see, so what is the tension? Tension is larger at this point, it is smaller at this point. I can just find out what is the effect on all of them, okay, on the time period of rotation. You can do all these things over here. And then the centripetal force, you can also estimate what is the centripetal force. So you can bring it nearby to here, okay, and so on. So this is what you can find out from here, right? So all this you can do it interactively. You can design the questions appropriately and you can work on this. Next, this is really wonderful. So let me drag it a little bit here, right? So you have a person here, and it's not a person, this is just the pivot over here, and there are two objects instead of one object. There are two objects over here. They are now made to move in a circular path, and there's a plot of acceleration versus time taken, and you can vary anything over here. Initially, there is no motion being seen, and then what I do is there's no start button or anything, and this omega plus, omega minus, which means you can increase the omega, you can decrease the omega. In a similar way, r plus and r minus, it tells me you can increase the radius or decrease the radius. Initially, this button is for resetting, so it is mean to the default state, and I can increase this when I increase this. Let us say, for example, I make r plus over here. Now, what has happened? The objects are moved a little bit farther away. Okay, so 2.25. Okay, so it is now increasing. Make it as 2.25 over here. Okay, now what does this do is that when you make it 2.25, initially it was 2. You made it 2.25. It takes some amount of time to start from 2 to 2.25. In the meanwhile, what happens to the acceleration? Okay, that's what it does. So it does not directly give you that value, but it gives you something like this. Now there is no rotation, so therefore, what is the acceleration here? So time axis is increasing. You can see 30.2, 31.2, all this is increasing, but the value of A is not at all increasing. There's no curve, there is no plot, nothing, which means there's a line here, the purple line, the black line that you can see, it is increasing along this axis. What is this axis? 0 here. That means the acceleration is 0. There is no acceleration. Now, if I want to set the acceleration, what should I do? I should make it rotate, right? Now, how do I rotate? I increase the angular velocity. Let me increase it from here. Omega plus, I make it 0.25, and this is increasing in terms of 0.01, 0.02, and so on, slowly, and then you see there's a slow increasing line, and this is started to rotate. See, a simulation is not something like only to watch and it should be attractive, it should be flying and so on. Okay, it should reveal some information. In that aspect, I rank this particular simulation to be number 1 because it gives you a lot of thinking. Okay, it helps you understand how things change, right? Now what I do is, let me increase this value. I'm going to keep the same radius. I'm not increasing the radius over here. I will now put this over here. I will increase the omega once again. Now what's happening once again? See, the omega is increasing, and you can see the acceleration is also becoming higher and higher. Now what I'll do is I'll abruptly change the value of omega. Instead of taking 0.5, I'll make it as 2 now. 0.1, 0.25, 1.752. When I do this, it takes some time for it to get adjusted to that. And the meanwhile, how does the acceleration increase? 1.86, 1.89. So it takes something like this. It takes a curve like this, and then it saturates, and finally it reaches 2 over here. The moment it reaches 2 over here, the acceleration seems to be a constant. What is the value of acceleration here? This could be around 0.8, 0.9. Now what you can do, ask the student is that, why does this variation happen? So how do you calculate this G? This is not your something like what do you call your linear, not your rotational acceleration, it's a linear acceleration. What is the name of the acceleration? And you see, when I increase this one, there are 2 red arrows being observed here. Why do you get those two red arrows? What does it denote? Why are there two red arrows? Usually when I do a circular motion, there's only one arrow being seen, but why are there two arrows, right? So many questions can be asked. The fundamentals of it can be questions and they will be able to answer this. Okay, so this is what is the interesting thing about this. Let me move on to the next one. Now this one, let me see what is this. It has radius mass g. Now comes the vertical circular motion. Okay, so far we have been looking only at the horizontal. Now we will come to the vertical circular motion. So where is the E? There's a start here. When I click on the start, now what happens? The particle is moving like this. Okay, so this is a wonderful start for introducing the circular motion. That is here, vertical circular motion. Now what's happening over here? I made it as a slow over here, so it's moving like this. So it's a pendulum, and some amount of force is being given, so it is oscillating like a pendulum. What I will do is, let me increase some parameters here. How do I increase the parameter? I have to increase the parameter here. Initial ball height. Okay, I took the ball height to be a height of 0.25 meters. What was the radius? The radius was 0.7 meters. This height is 0.7, but I took it only to a height of 0.25. So it did not move faster. So I will increase this. I can't increase that. Okay, let me increase it. Okay. Let me. Okay, let me keep this one here. I don't know why I'm not able to raise this one here. 0.25. Earlier it was 0.2, right? Okay, now it is made 0.25. Okay, it takes some time, I think. A bit glitchy over here. Okay, I will increase the speed over here. Speed at the bottom of the circle. Now here the speed at the bottom of the circle is seen to be 2.236. Let me increase this. When I made it, it's 2.919. I'll make it a little bit faster. No, it's already the same speed. What do you find now? You see, it has gone to a much more larger height, right? When you increase the speed, the height is larger. Though there are some arrows, we'll see those arrows, what is happening over here. Let me increase it to a much more larger. Now what's happening? Okay, that means at this point, the speed was much higher. It is going until that level, right? It has crossed the median over here. The center of this, it has already crossed one radius over here. Let me increase it a little bit more also. Now what's happening? Suddenly it fell down. So what happened? So it goes from here. Let me reset this. Let me redo it once again. I'll increase it to something like this. It goes to that level and it falls down, right? So what is that falling down means? So before asking or answering that question, let us understand what is given by the arrows over here. So there's a red arrow which is shown, which tells you about the tension acting on it. There's a F centripetal, the blue color one over here. See, the tension and the centripetal force are varying in a vertical circular motion. First thing, okay. And secondly, now you see, so where is it larger, where is it smaller? That we need to look at it here. When it comes to the center over here, the tension and the centripetal force are larger. You should ask the question, so why does it increase at the center? And as we keep on going away, why does it reduce? Okay, now what I'll do is, now if I increase this a little bit, I give a larger force, it crosses this, and I expected this to complete one circle. It's not completing, but it suddenly fall down. Why does it fall down? Why does it fall down? That's the question we need to ask. Or what is the minimum velocity that I would like to give so that it keep on going like this and reaches the topmost point? Let me increase it to this much. This much. Now what happens? Again, it went until that level. See? It went until that level. See, here it is crossing. It went until this much and suddenly it fell down from here. Now we need to ask, okay, what is that velocity that we should provide so that, okay, it is able to complete one full circle? Or even the math behind it. Okay, experiment is shown, but you should show us what's happening over here. Now, while it falls over here, what kind of motion it is describing? It's describing a projectile motion, right? So you can ask so many questions over here. Let me increase this. Now it is 5.691. I will increase a little bit more. 5.874. Wow, it is describing one full circle, right? While it describes one full circle, now let us look at what's happening to the forces acting on it. The forces acting on it, as you see, it again came down. It did not describe one full circle. So tension was here. Let me increase it a little bit more. Just completed it. And let us see whether it completes a full circle once again. Fingers tried. Yes, it completed. Okay. Now let us see what's happening to the tension and the other force acting here. Now, when the bob is at this point, tension is almost zero. Okay, it is not zero, it is some value of it is being present over here. That means when it comes here, there should be some amount of tension. If I reduce it, when it falls over here, let us understand what is happening to this arrow. Let me now reduce this velocity here. Let me keep it somewhere over here. What's happening to tension? Keep careful note. See, the moment the tension becomes zero, then there is no pulling force, and automatically the ball or the bob is under the mercy of the gravity or influence of gravity. It has to fall down, right? When tension becomes zero, it falls down. Very, very important thing. So you can explain this to students. When does the bob actually lose contact with the circular path, vertical circular path? When will it describe one full circle? When it will not describe one full circle? These kinds of questions can be addressed over here. Then, now, let me increase it to this much over here. Or maybe I'll keep it over here. I'll keep it here. I'll keep it here. Okay, 4.712. And value of G, I'm not going to change. Okay, for some reason, maybe if you want, you can change it. And let me increase the mass. Becomes more massive. Okay, if it becomes more massive, and I increase the speed at the bottom a little bit more here. Where did it lose its contact? It lost its, or maybe when did it complete one circle? It completed a circle somewhere over here. 5.587 something it completed, right? If I keep it over here, will it be able to move? It did not move. Lost its contact, right? So therefore, somewhere mass also plays an important role. So we need to ask the question, so how does the tension, how do you calculate tension in terms of mass, the velocity at the equilibrium position, and also the radius? Okay, I can also change the radius. If I reduce the radius, then what will happen? Will it be able to complete one full circle with the same velocity? Earlier it was not able to complete. Yes, of course, it's completing one full circle, right? So it doesn't lose the contact anywhere over here. Okay, so therefore, so somewhere radius also plays a role. Now you ask a question, so under what conditions does it depend? What is the math connecting these relationships? Okay, one of the wonderful simulations that I can see for vertical circle simulations. Okay, you can ask n number of questions on it, and the students will be able to answer this. Right. If they are able to answer this one, any problem on the circular motion, they'll be able to easily solve it. Let me close this also. Now comes one more interesting thing. It's a roller coaster method model. Here we are not going to calculate anything. Here we are just going to show, okay, what happens in a vertical circular motion, what happens to the tension, centripetal force in a much more amusing way. So what's happening over here? Let the card start from here. Velocity is like this, mg is acting downwards. Is the mg value changing? Mg value is not changing. See, the green arrow is never changing, whether it is moving on this slide or maybe in a circular path or maybe it is going upwards. This value is never changes. Okay, next is, let us look at the normal force over here. Normal force is acting over here. This also never changes. But the centripetal force is acting over here when it is in a circle. Now what about here? So there's a normal force acting over here. Centripetal force and normal force are equal. It provides the same thing over here. There's one more arrow here, velocity. Now what is happening to velocity? Velocity, okay, is seen to be almost a constant every time. Length of the velocity is same. Now as it climbs upwards, what's happening to this? Velocity, well, length is not changing over here, which means maybe there is an engine or something which is making it to move across, right? So if there was no engine acting on this, then definitely the velocity vector would have changed over there, right? Okay. So this is what one can understand. How does the vectors actually change, especially the normal force and centripetal force? How do you write the directions? That is very important. You can understand from here. Let me close this. Okay, so this one. Now, so far what we have seen the applications of circular motion on various branches of physics. Now we are seeing one more, which is on SHM. Can I rotate this? I'll not be able to rotate. Now what's happening over here? You have some particles, okay, which are now moving in a what you call on a path like this. Okay, that is a to and fro motion. They're exhibiting an SHM over here. If I look at it from a circular point of view, the same thing. Okay, as you see, it appears when you put it in a circle, then maybe you can move this one in a slow motion, so you'll be able to see. Or maybe I'll just rerun this wave and run this a wave. See, so it is moving like this over here. And if I move it in a circular view, this is what happens. Let me see if I can do it in 3D view. Wow, I can do it in a 3D way, but I will not able to move it here. That's the problem. Okay. So anyway, now you can see it in a 3D view. See the particle which was moving like this. Okay. If I look at it from a two-dimensional view, it appears to me the particle is oscillating like this. But from a three-dimensional view, I observe that this oscillation can be converted into a circle. Which means that, why is it important? Which means that the equation that we use for an SHM and the equation that we use for a circular motion is almost the one and the same. There also in an SHM we use something like y equal to a sin omega t. Okay, here also you can use a similar thing. We use y is equal to a sin omega t to describe a circular motion. And SHM, okay, in 2 dimensions, if you consider the mapping of an SHM in 2 dimensions, mapping of a circular motion in 2 dimensions, okay, will give rise to 2 independent SHMs. Okay. Now what is this? Circular motion as applied to a magnetic field. Now in a magnetic field, let me reset this. Now this is the magnetic field. What's the direction of magnetic field? Direction of magnetic field is inwards over here. Now there's a positive charge, there's a negative charge, there's a neutral charge. Now what happens when these charges are being put across, and how does the particles exhibit a circular motion? When you are teaching after circular motion, when you're teaching the magnetism part, then you can bring back the concept of circular motion over here, and you can show what's happening over here. You can click on this play over here, and this is what is happening over here, right? So it moves in a circular path. This is something like a fundamental thing which we all teach in our physics. There's nothing new in this. Okay. Now what we can change here is maybe I can change the value of Q here. Okay. I can make all of them Q, and I can make 2Q if I make it 2Q over here. Okay. So this is one is 2Q, the other one is Q, I think. And then if I play here, now all of them are Q only. Okay. And what happens is, no, sorry. The one is Q, other one is a 2Q, the other one is a 3Q. Q is the inner one, 2Q, and then 3Q. Okay, you can find out. I'm sorry, it's not, Q is not A1. So what do we have here? MV squared by R should be equal to BQR, BQV. So you should have V cancels on other sides. R should be equal to MV by QB. Okay, R equal to MV by QB, or R is inversely proportional to Q. Right? Yeah. So larger the value of Q, lesser the value of radius. So which means that the inner one should be 3Q, next one should be 2Q, outer one should be Q, right? So this is what it will be helpful. You can understand this. If you increase the velocities over here, there are 3 charges given over here, and you increase this. Oh, it's already given. I didn't see this. This is V, 2V, and 3V. This is V, 2V, and 3V. Now what happens to this one? When I click on this, now you see it depends on this. Now how you can put it across, if suppose if you are teaching circular motion after you teach magnetism, usually we don't do it. Okay, but if you want to come back, and then what we can do is we can say the circular motion is nothing but is a result of when the velocity of the object, the direction of velocity of the object, and the force, if they are mutually perpendicular, then you can see there is a circular motion being exhibited. Now how can you make them mutually perpendicular? You can connect a stone to a string and make it rotate. When you rotate it, the pulling force is tension, which is acting downwards, and velocity is like this. So tension and velocity are perpendicular. Now what are the other ways of rotating? The other ways to rotate it is there should be a driving force, okay, and there should be also be your the mv square by r should be equal to driving force. So here what happens is, okay, you have a magnetic force which is acting towards the center, and the velocity which is acting like this. So it describes a circular motion. You can put it across like this also. But when the angle between the force and the magnetic field is changing, let us say for example, if I put parallel to field, okay, and if I play it, what happens? It goes in a straight line over here. So then once again, your magnetism comes into play over here. Okay, let me close this. Cyclotron. Cyclotron is not there in our syllabus. For CBSE, we do have it. But anyway, I thought this would also be interesting. I do teach in my class. When I do this, I actually draw it in the board and I show them what happens. Okay, how does it work with this? So the mode, acceleration, voltage, everything is being given over here. There are 2 Ds over here. And let me start this. Where's the charge? Charge has been kept over here. When I click on this, it starts spiraling. Why does it spiral? What is the effect of electric field? And when it goes outwards, what happens? Everything I put it across. So nicely, wonderfully described. Okay, if you use this one to describe, you can make a child understand the effect of circular motion due to electric field, due to magnetic field, and also what happens when it comes out, what is the energy of it. Everything can be put it across. If you even derive the equations over here, wonderfully, you can put it across. Okay, what happens to kinetic energy, and why do we need a cyclotron? All these things can be put across here. Okay, So thus we have come to the end of all the other simulations except for these two. Let us do that also. For that, let me go to this also. This is not circular motion. This is something like Kepler's second law. Okay. So wherein what we do is you have a particle and it moves in a elliptical orbit. And then what happens to different values of the radius, second radius or aerial vector. You can do all these things over here. So this also you can use it. Where is my start button here? Run button here. Now this is shown over here. So what does it tell you? There's something like arrows, the lines which have been shown over here, which tells you can take up this area and you can find out what is the time taken. The area divided by time you can find out. You can do all these things using this. Okay, you can change the initial speed of planet. When you are describing Kepler's law, this could be very much useful. Okay, maybe can I put this across in a circle? Initial speed is 3.5. I think it's almost in a circle. And then in a circular motion also, do you think this rule would be applicable? You can try it out with this also. Okay, I'm not going into detail because it's a bit off topic. So I'm not going to into this animation speed. I'm not going to change anything over here. Okay. Okay, so this one is not a simulation, but instead, this is about a video which I found it in YouTube. Okay, this is once again a circular motion. Don't mistake this for a vertical circular motion. It's a horizontal circular motion. Let me play this. I have muted the video. I'll just put the link. Okay, also I'll show it to you. So you can just watch the same video. I can show it to your students also. This is called sometimes as the wall of death or barrel of death. In the previous Soko's book, a numerical was there, okay, in the same this one concept. So as you see here, there's a vertical cylinder being placed over here, usually made out of wood, this one bamboo, and or maybe some other material which has a lot of friction. And you can see there's a window over there, and through this door, the motorbike people or people, motorbikers and cars, will enter through this and they will start climbing this barrel. Okay, and as they start climbing this, okay, they will not fall. Okay, and they keep on moving circularly like this, and in such a way that the centripetal force equal the normal force, and the gravity and the friction, okay, would be equal and opposite. So as a result of it, they maintain a perfect balance. I'm just not going to show the full video because the full video is around 8.56 minutes. You can watch it on your own. So this is one of the stunts which has been shown. Let me just fast forward it a little bit more and see like how do they actually go across. Okay, so in between our artists have already come in between. Let me just close them also. Right. Okay. So you have seen one bike which has been climbing up. Let us see a few more bikes which is also climbing along with it. Right. See, there are around 3 bikes which have been moving across. 1, 2, and 3. They're all moving in the same horizontal circle. Right. And then if I go still more over here, I can see the cars also will start climbing. See, the cars are also start climbing. See, wow, wonderful stunts they actually do it over here. So this is what you can observe. Students will really be happy to see such kinds of stunts. You know, so this was seen in some of our olden days in white. We were children, and in our villages, shows like this used to happen. Okay, nowadays it's very difficult to see this because people have got hooked to OTTs and as well as to mobiles. So we will not be able to find this, and the only way to find these kinds of things is only through these videos. Thanks for those who already create such kinds of videos. Okay, and one can really explore a lot of physics into it. Okay, so we can actually draw the free body diagrams here itself and show like what is a normal force with the friction acting. We can show all these things. And in fact, what you can do is I have tried this in my earlier school, something like I take a tube and I put across an object into it and I keep on circulating it like this. Okay, as I keep on moving it across, I observe, okay, the object does not fall down, it keeps on climbing upwards. So the same way I can see, look at the stunts over there. So the car fellow and the biker, they both join hands with them. Okay, so it's not advisable to do this one, okay, at home or any other place, because these are all professionally well-trained people. They can do it easily, but okay, we will not be able to do all these things. Okay, so fine. So then, right, so all this, they used to go around, they used to stop and so on. Okay, so with this, I think we have come to an end to my simulations video, which completely showcased on what kind of simulations are there to run across for the circular motion. Circular motion is an easy topic to first initially look into it, but if you look at the math behind it and ask them to solve questions based on it, many students make a mistake. In fact, if you ask me, do we really find time to do all these things? I will say no. But sometimes, we need to find some time and we can create some assignments based on this. See, I always believe in the more the exposure that you have, the more creative you become. Okay, so what happens is when we talk about simulations, we generally look at only the normal type of simulations from PHET or O physics. Even I was not aware of so many simulations that are available. But as I started looking into it, I also gathered some interest to look into like what are the different kinds of structured problems we have. Can we learn all of them through visual? So I can rather say simulation, I can say it's a type of visual physics that we are learning. Okay, so this visual physics learning really helps me out, okay, to putting up the concepts in a different way. And that's the reason why I started making out these videos. So do share these videos with a lot of people, whomever you know, your teachers, your fellow colleagues, and so on. This will really help me out. It'll prove this as an encouragement for me. I'm not charging anything, nothing over here. So with this, I would like to end the session. So you can also let me know if you have any other ideas in mind. Initially, I thought of doing something like ATLs, then what is your profile, learner profile, how to look into it, and so on. I've also made a video based on it, but later on I thought, okay, anyway, you're all IB teachers. Okay, so IB teachers know everything. So what is the point in reiterating once again? So there's no point in doing that. I thought, okay, so technically let us look into it instead of doing this one. So I started doing this. So thank you for being with me, and let me see you people in tomorrow's videos. Thank you.